The Paradox of the Ravens, a deep dive into confirmation in science. Hello, my name is Mark Lang, and I am an educator at the University of North Carolina at Chapel Hill. Today, I would like to discuss an intriguing concept known as the paradox of confirmation, which is often referred to as the paradox of the ravens. This term was coined by the philosopher Carl Hempel, who first illustrated the paradox using an example involving ravens. The essence of the paradox of confirmation revolves around the idea of how hypotheses, whether in scientific inquiry or in our daily lives, are validated through our observations. To illustrate this, think about the classic detective stories where a detective meticulously gathers evidence to support or refute various theories regarding who may have committed a crime. Typically, no single piece of evidence is sufficient on its own to definitively identify the perpetrator. For instance, a specific clue might lend some support to the theory that the butler is guilty, thereby confirming that hypothesis to a certain extent. This confirmation can vary in strength. It might strongly support the idea or only provide a slight indication of the butler's guilt. Conversely, a piece of evidence might contradict the hypothesis, suggesting that the butler is innocent, which would be termed disconfirmation. Again, this disconfirmation can be either strong or weak. There is also the possibility that a piece of evidence is neutral, offering no support or contradiction to the hypothesis in question. The paradox of confirmation raises an important question: what criteria must be met for a piece of evidence to confirm a hypothesis rather than disconfirm it or remain neutral? The paradox begins with three seemingly reasonable premises and leads to a conclusion about confirmation that appears quite counterintuitive. Let's delve into the first of these three premises, which I will refer to as instance confirmation. Imagine we are evaluating hypotheses such as all lightning bolts are electrical discharges, all humans possess 46 chromosomes, or all ravens are black. Each of these statements is general, taking the form all Fs are Gs for some F and G. The principle of instance confirmation posits that if we are testing a hypothesis of this nature and we find a specific instance of F that is also G, then this evidence supports the hypothesis to some degree. This notion seems quite reasonable, doesn't it? The second premise is known as the equivalence condition. It states that if we have two hypotheses that convey the same information about the world, meaning they are equivalent in that both must be true or both must be false, then any evidence that confirms one hypothesis will also confirm the other. This idea should resonate as quite plausible. Now, let's focus on our example hypothesis: all ravens are black. The third premise suggests that this hypothesis is equivalent to another statement, which can be awkwardly phrased as anything that is not black is not a raven. To clarify the equivalence of these two hypotheses, let's rephrase it. The assertion that all ravens are black essentially means that if something is not black, it cannot be a raven. This equivalence is crucial for understanding the implications of the paradox of confirmation. Let's explore a thought experiment involving ravens and colors to understand a fascinating paradox in logic and confirmation theory. Imagine we start with a hypothesis that rules out one possibility: a raven that isn't black. This leads us to consider another hypothesis: all non-black things are non-ravens. These two hypotheses are equivalent and amount to the same idea that there are no non-black ravens. Because they are equivalent, they must also be equivalent to each other. Now, we're ready to dive into the paradox of confirmation. Take the hypothesis that all non-black things are non-ravens. This is a general hypothesis that follows the form all F are G according to the concept of instance confirmation. This hypothesis can be confirmed by finding an F that is also a G. For example, if I observe a red chair, which is a non-black thing and not a raven, this observation slightly confirms the hypothesis that all non-black things are non-ravens. This is the essence of instance confirmation. However, here's where it gets interesting. The equivalence condition tells us that confirming one equivalent hypothesis also confirms the others. So, when I observe my non-black, non-raven chair, I'm also confirming the equivalent hypothesis that all ravens are black. This might sound counterintuitive because it suggests that I can confirm a hypothesis about ravens just by looking around my room and observing non-black items that are not ravens. The challenge this presents is that one of three things must be true. Either one of these hypotheses is false in a way that explains how we arrived at a false conclusion, the conclusion does not actually follow from these hypotheses, or the conclusion is true despite seeming false. It's up to you to ponder which of these options is correct. This paradox reveals the complexities of confirmation and hypothesis testing, especially when dealing with equivalent hypotheses and the nature of observations.